Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will introduce the coefficient of determination. Okay. We will use r square as notation for the coefficient of determination. Now, the model that we are considering here is the classic simple linear regression model. yi equals beta 0 plus beta 1 x plus epsilon I. Okay. Now, I want you to consider this deviation of an observation with respect to its mean. Okay, so that deviation could be broken down into two deviations. We could, from an algebraic standpoint, what we're doing here is we're just adding a 0, right, plus yi hat minus yi hat, that's a 0, but this guy represents our prediction using that model, right, after we come up with our estimates for beta 0 and beta 1. Okay. So anyway, so that deviation of an observation with respect to its mean, and this shouldn't have an I because it's an average, right? Okay, so could be broken down into two deviations. One, an unexplained deviation, an error. Can you see that? That's the observed minus predicted. Okay, and an explained deviation, meaning regression deviation. Okay. Okay. So what we're going to be doing next is we are going to square these three differences for all the n observations in our sample, and we're going to add them up. Okay. By the way, this is the way that you would think about these deviations in plain English. You have a total deviation, and then you are, again, as we said, you're going to break it down into two parts: the error deviation and the regression deviation. As I said, what we're going to be doing next is squaring those deviations and adding up for all of those n observations. Okay. Now, this is something called the total sum of squares. Okay, and the notation is SST. You have also seen a different notation in your textbook to refer to SST. You have seen SYY, right? Okay, and this you have seen before when we talked about the estimation of sigma square, right? SSE, the sum of squares for error, and this, the difference between yi hat and y bar square, right? The sum of those deviations, we're going to refer to those as the sum of squares for regression. By the way, just saying that you have seen something like this before. Some of you prefer obtaining SSE as as SYY minus beta 1 hat SXY. So it's a similar situation here, right? This would be SYY minus beta hat SXY equals SSE. Okay, so it's just another way of expressing that, okay, but this will be important for the interpretation of the coefficient of determination. Anyway, so what we have here is total sum of squares equals SSE plus SSR, where this is the sum of squares for the error, this is the sum of squares for the regression. By definition, the coefficient of determination will be the ratio between SSR and SST. Okay? Now note something. Since SST equals SSE plus SSR, right? The total sum of squares equals sum of squares for error plus sum of squares for the regression. If we solved for SSR, we would have SST minus SSE, right? So if you substitute that here and then do the algebra, it would be SST divided by SST 1 minus SSE divided by SST. That would be the coefficient of determination R square. Okay, and the coefficient of determination can be interpreted as the proportion of the variation in y that is explained by the regression relationship of y with x. Now, I want you to remember something else. Remember when we talked about rho square? When we talked about rho square, what we ended up showing is that rho square is equal to 1 minus sigma square divided by sigma square sub y. So this guy r square is going to be our estimator for rho square. Make sense? Okay. Now let's use it. Okay, let's see our lecture notes. We have an example. We have talked about this example in another video. Remember, it's a data set about used Toyota Camrys. Okay, so in this case, what we want to do is to compute the coefficient of determination. Okay, so let's launch R and let's copy and paste what we have from this example. This we have done before. Remember, we have read the data, imported the data into R, and then what we did is we obtained the names of the variables involved, and then we also asked R to remember those names so we can use them later. We can refer to them later, right? Let's see, everything seems to be working fine. Now let's fit a linear model. Again, we've done something like this before. The response variable is price, the predictor variable is odometer reading. Let's see if we use that summary command. We have this, right? So we know that this is going to carry out the two-sided hypothesis test, right? And usually we're interested in saying something about the slope parameter. Okay, it is significant, meaning we have evidence that it's different from zero. Okay, it's a two-sided alternative. Okay, now see that R squared, that's the determination coefficient, right? And again, this guy, I remember what we said, this guy represents a percentage of the variation in our response variable that is explained by the linear regression. So in our case, in this example, with our simple linear regression model, we're able to explain roughly 65% of the variation in y. The remainder of the variation, roughly 35%, is unexplained. That's due to random fluctuations, to error, right? And again, just like before, remember for the theoretical one for rho square, right? We had 1 minus sigma square divided by sigma square sub y, right? And we said the only way that rho square can be 1 is when sigma square is 0, right? That means that the variance of the epsilons is 0. But if that's the case, we have no variation. We have a perfect linear relationship, right? And in this case, we know that this guy is the sum of squares error divided by n minus 2 is going to be an estimator of the error. So the only way that we could end up with an r square equal to 1 is if there's no variation, right? If all the points are on a straight line, okay, perfectly aligned. Okay, so going back to our example, this is what we said, right? That r squared is roughly 65%, right? That's the variation that we can explain using this simple linear regression model. The remainder, as we said, roughly 35% is unexplained. And just a reminder that the higher r square is, the better, and we know that the highest value that you can have for r square is 1, right? And yeah, that's basically it. R square will measure the strength of the linear relationship that we have. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.